In this video, we're going to talk a little bit about the idea of variability and what relates to a concept called the flaw of averages. So suppose for a second that I asked you, or I said, I'll give you $1,000,000 if you go decide to walk across a river that is on average 3 feet deep. Would you do it? Let you think about this for a second. So you might want to pause the video. Well, it turns out that this probably is not such a good idea because, as we call it in the land of statistics, we call this the flaw of averages. That in essence, if the water is on average 3 feet deep, that doesn't take into account an important aspect. Well, the reality is the water may be only, I don't know, a couple inches shallow all the way across, but all it takes is this one area right here where the depth suddenly drops to be quite extreme. And that's called the flaw of averages. And the flaw of averages basically states that you can't just take the average into account. You also have to have a measure of spread within your data. So we need some measure of spread in the data. Okay, well, we're going to account for that, and we're going to talk about a couple of different things that are from simple to a little bit more advanced. Now, interquartile range we won't talk about, but that's one way to describe how spread out the data is in the data set. There's something called range, which is really just a quick concept. And then probably what we use the most often in statistics is the idea of variance and standard deviation. Okay, so let's just say we have some quarterly earnings here, and these are the quarterly earnings, and we want to summarize the data. Well, we know that we can take a sample average, since this is maybe just a sample of our quarterly earnings, and we can look at if all of the earnings were to be the same, what would they be? Well, that's exactly what the average describes. So 70 plus 30 plus 10 plus 20 plus 40 plus 50 divided by 6, and that gives me 100, 130, 170, 220 divided by 6 is going to be, let's see, 220 divided by 6 will give me about 36.7. So 36.7 million earned on average, right? So that sounds pretty good. But it depends on what quarter you're in, right? Because if you were over here in the third quarter, you'd say, oh, we didn't do very well at all. And if you're putting all your eggs in the basket saying, well, I expect to come close to my average next year, you may be either grossly disappointed or extremely excited. So we need to summarize this data in terms of its spread. Well, one of the things that makes sense is to look at the smallest and largest values. So we could say, okay, the smallest value, or the smallest earning that we've ever had, or within this data set, the quarterly earning was $10 million, and the highest was $70 million. So we have a range of $10 million to $70 million. And that's a good way to summarize the spread of the data, right? That shows us how spread out it is. We're all the way on the scale from, okay, well, maybe here's our average, which is 36.7, and then down here is 10, and up here is 70. So we're on average, we're actually shooting closer to our lower bound than we are to our upper bound. Well, why is that? Well, because we have 20, 30, 40, all of which are, well, 20 and 30 are closer to 70, to 10, and 40 and 50 are closer to 70. So we're a little bit closer to our lower bound than our upper bound. Okay, so how about another way to summarize the data? Well, we want to definitely look at other notions of spread. So one thing I can do is I can plot the mean on a number line, which we said was 36.7, and I can start to take into account these things called deviations. So each point has a deviation, and the way we define a deviation is it's the difference between the value and the mean itself. Okay, so if I have a value of 70, which is this point somewhere over here, now 70 has a deviation. Well, what is the physical representation? It's how far away it is. Okay, well, if the x value is 70 and my mean is 36.7, then the difference is going to be, let's see, 33.3. Okay, so we can say, now this is positive, so basically we can conclude that 70 is 33.3 units higher or units above the mean. Similarly, if we have this value of 10 somewhere down here, so there's my point of 10, its deviation, well, we always want to be consistent. We don't want to do just subtract in the way that makes the sign positive, because we want to use the sign to describe where it is in reference or in relation to the mean. So 10 minus 36.7 tells us that this particular value is going to be negative 26.7 units away from the mean. Well, what does negative mean? It just means it's below the mean. 10 is 26.7 units below the mean. So each point has its own deviation. Now, we want to summarize those deviations. We want to kind of take, if we have an x bar, which is an average, then we also want to have some sort of measurement of some sort of average deviation, if you will. So what we call that is the standard deviation. And roughly speaking, very roughly speaking, standard deviation is the average, quote unquote, amount of spread. Now, if we're going to be representing our measure of central tendency as an average, then we also want to be describing the amount of variability in the data set in terms of a average or some sort of average. It makes sense, right? If you're going to use an average to represent the center, then you kind of want to talk about how spread out your data is with reference to some kind of average measurement. So we'll do that briefly, but I want to make a quick distinction again here, and we've encountered this in prior areas. But a population has a measure of, if I had data on an entire population, then I could compute a mean and I could compute a standard deviation. Okay, well, the symbols that we give the mean when we're computing it for a population are mu, and that's the Greek symbol. So this is pronounced mu, depending on how you want to say it. It's actually spelled mu, but that's the symbol what we use to represent the mean. And standard deviation is the symbol sigma, and that is sigma. So that's just what we use. If I'm saying sigma equals 6, that means my population has a standard deviation of 6. And similarly, now oftentimes in statistics we draw a sample because it's cost prohibitive to take everybody in the population and do a census. So we also get data on the sample. Well, the sample is going to have a mean and a standard deviation of its own. Probably not the same as the population because we're going to have some bias in it and so on and so forth. But we're going to call that x bar. Okay, that's what we've been using. So that's the sample mean, and then S is going to be the sample standard deviation. Okay, well, notice the relationship here. Mu is the Greek m. Why we use x bar is beyond me. But sigma is the S in the Greek alphabet, and so we're using little s to represent it for a sample. Okay, well, let's talk about how we're gonna focus in on samples here. And so now we want to compute what we call the variance and standard deviation. So let's develop this. So for each, first of all, x value, I'm going to need to figure out how far away it is from the mean in order to be able to talk about a deviation. So I'm going to have to standardize the deviations. I'm going to have to get the deviations first. So each point is going to have its own deviation: 70, 30, 10, 20, 40, and 50. And each of these is going to have a deviation. Well, 70 minus 36.67, which we've already described to be 33.3. And then we have 30 minus 36.7. So this is we're taking the x value minus 36.7, which is our mean quarterly earnings. And now we have 30 minus 36.7. Well, that's going to be negative 6.7. And 10 minus 36.7 is going to be negative 26.7. And 20 is going to be negative 16.7, and 40 will be 3.3 units above the mean. So I'll just put pluses here just to indicate that some are below and some are above. And 50 is going to be 13.3 units above the mean. Okay, so you might say, all right, well, Milos, if you want to calculate an average deviation, then let's take the sum of all the deviations, right? Well, you can verify this, but guess what these are going to sum to? They're going to sum to exactly 0. And so if I take 0 divided by 6, well, that's not going to be very interesting. And guess what? They're always going to sum to 0. Why is that the case? Well, if we think about an average as being the value that all the data points would be. So if each of these, these were 6 friends, and the 6 friends each had this much amount of money, and they all put it into a pot and divided it amongst them equally because they're all good friends, each person would get $36.7 or $36.70. Okay, well, if you look at how much each person either put in, like this person who had $70 had to basically gave up $33.3 of his own, but the person who had 30 actually, actually had 6.7 less than the average, so that person got some money back. The person who had $10 got $26.7 again, so that everybody got the same amount. Well, all we're doing is we're redistributing these amounts so that the average is basically, again, the value that these would be if we redistributed everything equally. Okay, well, that means that if we add up how much each person gave up and contributed, it's going to be 0, right? Because that money didn't disappear and we didn't add new money into the pot. It just got redistributed. So every time we compute this, the x minus x bar, as we'll describe it, the sum of those x minus x bars is going to be 0, always. Okay, well, what options do we have? Well, we could ignore the sign. We could make them all positives and ignore the sign completely and then take the average of those. But for purposes that we're not going to describe here, this is more of a statistics class, it doesn't mathematically do well to try to just take the absolute value of these guys. So what's another way we could get rid of negatives? Well, another way we could do it is by taking the square of those deviations. If I square numbers, then that's going to leave me with positive numbers. So 33.3 squared is going to be about 1,109. I'm just going to round up. 6.7 squared is going to be about 45. 26.7 squared is going to be 713. About, again, I'm kind of rounding here. 16.7 squared will be 279. 3.3 squared will be about 11. And 13.3 squared will be about 177. Okay, well now I can add these together since they're all positive. And if I add these together, I'm doing this right off to the side here, plus 45 plus 713 plus 279 plus 11 plus 177, I'm going to get 2,334. 2,334. Now what is this number? Well, this is the sum of the squared deviations. So we write it like this. The sum of the deviation squared is 2,334. Okay, well now I can average the deviations, right? I can take the average of this because I'll no longer get 0 because I'm not, the sum of positive numbers is going to be positive. And so I have this figure which we often call the sum of squares for obvious purposes. Okay, now you might just say, let's take this number and divide it by the number of observations there are, right? Which would make sense. In other words, divide by 6. 1, 2, 3, 4, 5, 6 values. But the actual way to do this is to divide by 1 less than the number of values there are. Again, we're not going to talk about why. It's not going to make sense even if I do describe it. But this has to do with using samples to try to make bigger statements about populations. Okay, so this is the way this value is going to be described. So 2, 3, 3, 4 divided by n minus 1. Well, we have 6 observations, so 6 minus 1 is 5. And 2, 3, 3, 4 divided by 5 is going to be, let's see, divided by 5, it's going to be about 466.8. Or I'll just round it to about 467. Okay, so the sum, the average, roughly, that's why I said earlier, it's roughly the average amount. The average sum of the squared deviations is about 467. Now, wait a minute. This isn't a true average because we did square something. So at some point, it probably makes sense that we should take the square root. Okay, well, first of all, let me summarize on a clean slate here. So the variance, what we call the variance, it's not a measure that we use very often because the units are kind of funky. But the variance for a sample is going to be defined as, so it's called s squared. It's the sum of the deviation squared divided by the number of observations minus 1. Now this is how you can do it if you really want to do it in a table. We don't usually do it in table form, but this kind of, I think, gives at least a little bit of insight into how you would do it. Okay, so that's called the variance. And the reason we don't use this measure very often is because, okay, so first of all, x is measured in millions of dollars. So that means if I take an average, that's going to be measured in millions of dollars. So if I take millions of dollars minus millions of dollars, I still get millions of dollars. So each of these is still millions of dollars all the way down. And if I add up millions of dollars, I still get millions of dollars. But what do I get when I square millions of dollars? Well, I get millions of dollars squared. That doesn't make sense. That's not really a unit that I can make sense of. So then when I add up all the millions of dollars squared, I still get millions of dollars squared. And if I divide it by 5, I still get millions of dollars squared. So this right here is in millions of dollars squared. And that's not really a unit we can talk about. So the variance is a mathematical measure, but it's not a very practical measure. The standard deviation, on the other hand, says, okay, I want to get the right units. Okay, well, how do I get the right units out of millions of dollars squared? Well, if I square dollars, then I want to get millions of dollars back, then I should probably square root it. So, okay, if s squared is equal to that, then s is just equal to the square root of both sides, which is the sum of x minus x bar squared divided by n minus 1. So first you can calculate the variance and then take the square root of it. So that means right here what we have is s squared is equal to 467, and then s is going to be the square root of 467. And the square root of 467 is, let's see here, about 21.6. So about 21.6. Well, if you look at the data and you kind of think about this idea of average spread, now since this is in millions of dollars, this is kind of, this 21.6 gives me an idea of average spread. Well, on average, if you kind of think about 36.7 as being the mean quarterly earnings, and you kind of wanted to describe the average spread, you would describe it with the number 21.6. So let's interpret this. Let me back up here 1 second. Let's see. Okay, so if I have a mean of $36.7 million, and I have a standard deviation of $21.6 million, then I may choose to describe it like this. I'd say that on average, we earned $36.7 million per quarter. On average, that amount varied from the mean, right? Because it's a standard deviation, it's an average deviation from the mean by $21.6 million. Okay, and now again, this is not a true average, so we kind of put quotes around it, but we still describe it as the average amount of spread. So that's the idea of standard deviation, and it can be calculated in exactly the same way. If you were doing this in your calculator, let me pull up here my calculator, and okay, so if I were to use my calculator for this, what I could do is actually use, if you remember doing regression analysis, you could actually pull up your stat window and edit the data in there. And I'm just going to clear out list 1 here. Don't click delete, click clear. And now we're going to type in the various earning amounts that we have. So we have 70, 30, 10, 20, 40, and 50. Okay, so now I want to compute some statistics on it. Go to my home screen, clear out what's ever there, stat, calculate, and what I want to do is one variable statistics. So I have one variable, and that variable is the amount of quarterly earnings that I have. So I want to compute one variable statistics, and then I want to tell it where to go grab the data from. So notice that right above your 1 button, there's the L1. For me, it's in blue, and that corresponds to the second button, second L1, and it tells me everything about it. Well, there it goes. X bar is 36.7, and you'll notice that it actually tells you the sum of the values, which was 220. So that's before we took the mean. We had 220 divided by 6. The sum of x squared, we're not actually using that, so don't worry about it. It tells us that there's n equals 6 observations, and then s of x equals 21.6. Well, that's exactly what our standard deviation is. Now, we got a little bit of rounding error, of course, because, well, actually, we did pretty good. We got 21.6. And so then our standard deviation for the population is 19.7. You can get some more stuff out of it. It tells you the minimum, tells you things that are called like the quartiles, and then it tells you the max, so you could also gain the range from that. So you can get a lot of data out of this. Okay, so that's pretty much it for working with standard deviation. And so now we want to be able to ask some questions about it. Like, for example, if I know that the mean and standard deviation for a population, now we're dealing with a population here because we're talking about an entire class, is 85 and 20 and 75 and 5 for another class. Did class 1 really do better? Let's stop the video here, and we'll continue on in a separate video to kind of create a pause and to stop at a good point.